Aldol addition reaction. In aldol addition reactions, two molecules of aldehydes or two molecules of ketones can react together to form a product which has got both hydroxy group and as well as a carbonyl group in them. And the product that is obtained in the case of aldehydes is beta hydroxyaldehyde, where you can see that the hydroxy group and the carbonyl functional group are in beta position with respect to each other. If you take this functional group, this will be the alpha position, this is the beta position. And because you have the hydroxy group and as well as the aldehyde group in it, it is called as aldol. Aldol. This is coming from an alcohol, and this one right here is coming from the aldehyde. In the case of ketone, the product would be a beta hydroxy ketone. Let's now take a look into the mechanism for the aldol addition reaction using aldehyde as the starting material. Here, two molecules of aldehydes are going to react with together to form the product, where one molecule will be converted into an enolate to act as a nucleophile, and the other molecule will act as an electrophile. And this is going to be exactly the same even in the case of ketones. First, to begin with, one of these hydrogens will be abstracted to form the enolate ion. This will act as a nucleophile. So this is our enolate ion. Once it is created, it's going to make a nucleophilic attack on the electrophilic carbon of the other aldehyde. Let's draw the other aldehyde. This is another aldehyde. Now this nucleophile will need to go and find this electrophilic carbon and attack it and thrust these electrons onto oxygen. This will lead to an unstable tetrahedral intermediate, and here is the unstable tetrahedral intermediate. Then this oxygen with its lone pair of electrons is going to go attack a hydrogen from the water molecule to form the final product. Now instead of writing like this, it's better to connect all the carbons together so they can form the longest chain. So it will be easier for us to view. So here is our final compound, which is a beta hydroxyaldehyde. Now you can see in this compound, there is an hydroxy group and there is an aldehyde group here. Also, there is a new carbon-carbon bond that is formed between the aldehyde and the enolate. Ketones are in general less reactive than aldehydes, and therefore the aldol reactions with respect to ketones will be slow. Here again, it's going to follow exactly the same mechanism as what we have talked in the case of aldehyde. Let's go and abstract the alpha hydrogen from one of the ketone molecules to give us the enolate ion. So one of these hydrogens will be abstracted. That's going to result in a enolate ion. So here is the enolate ion that is obtained. Once the enolate ion is obtained, it's going to react with the second molecule of the ketone to make a nucleophilic attack on this electrophilic carbon. So this enolate ion will go and attack on this carbon, thrusting those electrons onto oxygen. And you can see that this is a new carbon-carbon single bond that is formed. Okay. And in the next step, this negatively charged oxygen is going to accept a hydrogen from the water molecule and get protonated. So this will go and abstract it to give us a final product, which is a beta hydroxy ketone. So this is the ketone functional group, and this one right here is the hydroxy group, and both of these groups are in beta position with respect to each other. The aldol addition reaction is again another example for a nucleophilic addition reaction because there is not a leaving group present. Say for example, this is a tetrahedral intermediate and none of these groups are going to leave, right? And because of which this oxygen is going to go grab the hydrogen and form the OH group. Now, when you count the number of carbons in the product, you can definitely say that it is going to be twice the amount of what we started with, right? Because 1, 2, 3, there are 3 carbons, 3 times 2 should have total of 6 carbons. 6 carbons. And another important thing with respect to aldol addition reaction is that it's generally reversible. So which means you have to remove the product as and when it is formed. from the reaction. The aldol addition product, that is beta hydroxyaldehyde or ketone, when heated in the presence of hydroxide ion, it's going to give us back the original aldehyde or ketone that we started with. This reaction where it gives back the aldehydes or ketones that we started with is called as a retro-aldol addition reaction, where the meaning for retro is backwards. Say for example, this hydroxide ion is going to go grab this hydrogen from the hydroxy group of the addition product, thrust these electrons to form the carbon-oxygen double bond, and this carbon-carbon single bond that is formed during the reaction will be broken to form the carbon-carbon double bond here to form the enolate ion. Okay, so you can see that this is one of the aldehyde molecules, and the other aldehyde molecule will be generated from the enolate ion, for which these electrons will come in, and this is going to go and obstruct the hydrogen from the water molecule to form the other aldehyde. So if you take a look at this, the product of the aldol addition reaction, so this is our first aldehyde molecule, right? And this one right here, which forms the enolate, will give us the second aldehyde molecule.